So let's go over question 1. A frequenter in a pub has used a random sample of 45 glasses of beer and has observed the volume of the beer that the barman has poured in these 45 glasses. And this person has looked at the average of the volume of beer that has been poured on these 45 glasses, and his goal is to be able to test a hypothesis. If the average of the beer that this barman pours on these glasses is half a liter or less than half a liter. Okay, so that's basically what this person wants to test. So basically our random characteristic of interest or random variable is volume of beer and the glasses. There's a volume of beer that the barman pours in a glass. Okay, so that's our random variable. And then, okay, so and then our null hypothesis is that this average is 0.5, and our alternative hypothesis is that this average is less than 0.5. So we assume that, or the person wants to test our hypothesis that the average of the volume of beer that this barman pours on each glass is 0.5, or no, this barman actually is not pouring enough, so it's less than half a liter. And can someone tell me that when you read the first 2 lines, this person takes a random sample of 45 glasses of beer and measures the volume of beer in these glasses, and then finds that the average of volume of beer in these 45 glasses is 0.47. Can you tell me what are the pieces of information that you can get from the first 2 lines of this problem statement?
We note that the average value is 0.47.
Okay, what about the first line? What is
the sample size is 45.
Yeah.
Size is 45, and then average of this sample is 0.47 liter. Okay, so these are important pieces of information. And then the other thing is that we also know the standard deviation is considered as 0.19 liters. So obviously, when this barman pours these beers in these glasses, it's not that every glass is exactly 0.5, right? It's going to be a little more or a little less every time. And the standard deviation associated with this variability is 0.19. So can you tell me, when you read the very last sentence of the problem, the standard deviation is considered as 0.19 liters. Can you tell me what is the notation for that? What is the notation that we use to show the standard deviation?
It's the I actually forget what it's called. It's not the S, it's the other one.
Sigma.
Sigma, thank you.
So this sigma here, this is important. Similar to what we have for the confidence interval, we had the same structure here. So this sigma is population standard deviation. Okay. This is important information that you have to find from the problem statement. So we either have the population standard deviation, or what is the other option? If I don't have the population standard deviation, what is the other option?
Sample standard.
Simple standard.
I may have sample
or samples
standard deviation. And what is the notation for that one?
Capital S.
S. Okay, so that's the notation for the sample standard deviation. So if you guys want to get a better sense as what do I mean by population standard deviation or sample standard deviation. So let's assume I want to measure the height, not that I want to measure, let's assume my research is in public health. So that's why all the examples come from public health. So let's assume in my research, I need to know the average of the height of all the people in the US. I need to know the average of the height of all the people in the US. How can I get that? If I had the luxury of going and measuring the height of every single person in the US and then look at the average of those numbers, okay, I would be able to find mu. So that would be the number. So this is what I call as population average, mu. And if I had that luxury to measure the height of every single person in the US, I look at the average and that gives me the mu, population average. I also, since I have the data already, I also would look at the standard deviation of all those measures. And that would give me sigma, which is the population standard deviation. Okay, so those would be the two values that I would get from the data that I would collect from every single person in the US. Average of the population and standard deviation of the population. These are the same notations in every statistics book in the world. Okay, so the same notations. However, there is no way I can measure every single person in the US in terms of height or weight or whatever I'm looking for. There is no way I can do that. What is going to happen? Then, if that's not the case, then I'm going to be able to, and let's assume in my research, I need to know this number and I need to know in this number. So what can I do? What I'm going to do is to take a sample of this US population or any population that I'm working on. I take a sample of this population and then I look at the sample average. I take a sample, I measure the height of every single individual in my sample, and then I look at the sample average. What is the notation for sample average?
X bar.
X bar. And if I measure the height of every single person in my sample and I look at the sample average, since I already have done the measurement and I have the data, I'm going to also calculate the sample standard deviation. And you guys just said that the notation for that is S, right? So that's sample standard deviation. So if I need to know mu and I don't have it, then I look at the average of my sample to be able to say something about mu. And this act of taking a sample, looking at the sample, concluding something about this unknown mu is called inference. It's called a statistical inference. Basically, this is whatever we did in module 7 and 8, with deciding something about the average of a characteristic of interest in the population, which is by looking at the confidence interval or test of hypothesis. Basically, we are making a statistical inference. And then also, since I don't have the standard deviation of the population, then I'm looking at using a standard deviation of sample to say something about the standard deviation of the population. Okay, so those are basically some estimation that I use. Okay? When we want to run a test of hypothesis, similar to building confidence interval that we looked at in previous session, when we want to test a hypothesis, always the very first important question, the very first question that you have to ask yourself is that, is the standard deviation of the population known, or standard deviation of the population is not known? If a standard deviation of the population is not known, then we take a sample and use standard deviation of sample, which we call S. We use that. So if the standard deviation of the population sigma is not known, we take a sample, we use the standard deviation of the sample. And then the formula that we are using would be different if we know sigma or if I don't know sigma. Similar to, remember for this confidence interval, we ended up with two sets of formula when we know sigma, when we do not know sigma. For the hypothesis test, it's the same too. Now tell me, let's assume I know the sigma, I know the standard deviation of the characteristic of interest in the population. And I want to construct, and then I take a sample of size n, and I'm looking at the average of the characteristic of interest in the population. Can you tell me how do I construct my test statistics? In both these scenarios, this is the test that I want to do. My H null is mu equals to something. My alternative is that mu, for example, is not equal to something, or mu is greater than something, or mu is actually less than something. So let's assume this is the test. This is the hypothesis that I want to test. Okay, so tell me how do you construct your test statistics? If sigma is known, this part. X bar minus mu naught divided by sigma over square root of n. Is this familiar, guys? Why are you not answering? Okay, so that's, and the notation for that was Z naught. This is what I call as test statistics. This is something that I construct using the sample I have taken, and using the average of that sample, I construct the test statistics, and I use that to make a conclusion if I'm going to reject the null hypothesis or if I'm not going to reject the null hypothesis. Okay, so that's that. And then can you tell me that for this other scenario, when the sigma is not known and we are using S, can you tell me how you construct your test statistics for that one? Divided by?
S divided by the square root of n.
S divided by square root of n. And this is what we call as T naught. Okay, so again, this is what we have as test statistics. So every time I take a new sample, every time let's say I take a sample of 20 glasses of beer, I come up with one average. If I take another sample of 20 glasses of beer, I come up with another average. I take a sample of another 20 glasses of beer, I come up with a different average. So every time we take a sample of a new sample, this average of the sample will be a new number. So this whole thing that I calculate here, this whole thing is a random number on its own as well, because X bar changes every time I take another sample. So then these test statistics that I put together has a distribution that we call as normal standard. And that's why we use Z table and all of that. So that's the standard normal distribution. And the same for this one. This random variable, every time I take a new sample, the value of the random variable X bar changes. I take another 20 glasses of beer and I measure the volume and look at the average is different. So every time I take a new sample, the average of the sample is different. So this whole thing is going to change every time I take a new sample. So this expression also x bar minus mu divided by s over square root of n is a random variable as well. And it has something, the distribution of this random variable is what we call as t distribution. This normal standard also is called as z distribution. If you may also see that as well. And that's why the notation for this test statistics is z and for this one is t, because that basically refers to the distributions that they come from. Okay, so it's important for you guys to be able to put together the test statistics associated with each one of these tests, because those are the ones that you're going to use to make a conclusion about the test, right? So then if it's if we have a two-sided test, let's say our our alternative test, alternative hypothesis, for example, is mu is not equal to mu null. The way to decide about this test is that I compare my test statistics with their critical values. Okay, if the test statistics z null is greater than z of alpha over 2 or minus z of alpha over 2, which I consider as critical values in the test, then we reject H null. And if it's one-sided, then I compare z null with z of alpha or minus z of alpha. We'll go over examples and learn, we give examples related to each one of them so we'll feel better. However, the same logic holds for a t-test. For example, if I'm doing a two-sided t-test, then when I calculate the value of this test statistic t naught that I calculated, then I'm going to compare it with t of alpha over 2 n minus 1 and t of alpha over 2 minus t of alpha over 2 n minus 1. And if the test statistics is in any one of these ranges, then we reject H null. Otherwise, and if it's one-sided, then I compare the test statistics only with one of the t of alpha n minus 1 or t of alpha n minus 1. Okay, if these are for one-sided tests. But as you can see here, these two are pretty much the same. So the only difference between these two is in the methods on the left, sigma is known, and the methods on the right, sigma is not known. And then if you can find that from a problem statement, the rest is just picking the right formula, plugging in the right numbers, and making the conclusion. So the very first important decision that you have to make when you want to answer any test of hypothesis question, similar to what we did for the confidence interval, is if sigma is known or not. And then depending on that, you pick the formulas on the right or on the left. Now, for this problem that we have in question 1, the standard, this is the problem statement, right? So this is all we have. So the standard deviation of the population is given to us. Should I pick the formulas on the right or on the left? The standard deviation of the population or sigma is given to us. Which one of the formulas on the right side of the blue line or the left side of the blue line? Which one of them I have to pick?
Left side.
On the left side. Okay. So let's, I'm going to repeat, let's go to the problem and just see how it works. So I'm going to repeat things one more time. So our null hypothesis is mu is 0.5. Sorry. And we took a sample of 45 glasses, and the average in this sample, which is X bar, was 0.47 liters. And the standard deviation is 0.19 as well. It doesn't tell you sample standard deviation is this. So if it doesn't, then that's the standard deviation of population, or that's sigma. Will you reject the null hypothesis at alpha? Alpha is 0.05. Okay. I want to decide on the test of hypothesis. Given the fact that I know sigma, I have to pick the formula on the left side because sigma is known. If I have to pick the formula on the left side, then this is the formula to construct the test statistic Z naught. So then Z naught is X bar minus mu divided by sigma over square root of n. X bar is 0.47 minus mu naught, which is 0.5, divided by 0.19 over square root of 45. And when we do the calculation, this number is going to be 1.059. And okay, now I have to compare that with critical values. Given the fact that this is a one-sided test, I have to compare that with minus Z of alpha. So let's go to the Z table and find the Z of alpha. And alpha here is 0.05. So I have to look at Z of 0.05. Z of 0.05. 0.05. Yeah. If we consider 0.05, oops, as this, so that's 0.05. So the Z that can give me this is minus 1.65. So the Z of alpha is always the positive value, right? 1.65. So that's the Z associated with 0.05. So minus 1. So the Z of 0.05, the minus Z of 0.05 is minus 1.65. So then what would you conclude then? This is the value of your test statistic, Z naught, and this is the value of your critical value. If your Z naught, the test statistics value, is less than the value of minus Z of alpha, then we reject null hypothesis, right? That's always the rule for rejecting the null hypothesis in this side, in this type of test. So, and here, let me correct this. This is, guys, let me correct here. This is minus 1.05. So this is 0.47 minus 0.5 in the numerator. So this is minus. So for the test statistics, guys, for Z naught, make sure to correct this. This is minus 1.059. And the critical value that I obtained also is minus 1.65. So if the value of our test statistics is less than our critical value, we are going to reject the null hypothesis. Now, can you tell me what is your conclusion here, given the fact that this is the value of your test statistics? So the value of the test statistics is 1.059. The value of the critical value that you have is 1.65. what is the relation between these two? The value of the test statistics is greater than your critical value. As a result, you fail to reject the null hypothesis.
What is that negative move over?
Which one?
Oh wait, it was negative 1 point.
Yeah.
That wasn't 0.4. Okay.
It's in the numerator, we have 0.47 minus 0.5. That's negative. That's where the negative comes from. Then we calculate the test statistics. Okay, so that's our conclusion based on comparing the value of the test statistics with the critical value. Now I have also asked you to calculate the p-value of this test. So what is the p-value? Can you tell me what is the p-value? That's probability of test statistics of z less than our test statistics. In this one-sided test, when this is the test, one-sided test, this is the formula for the p-value. And that's going to be the probability of z less than minus 1.059. Okay, let's go to the z table. Minus 1. I can write this to just round it. I can write this as minus 1.06. Let's find that. Minus 1.06. Minus 1.06 is this value. 0.144. Okay, minus 1.06, which is this column here. 0.0144. Okay, so that's the p-value. So the p-value for this test is 0.144, and alpha, the significance level, is 0.05. And let's assume, and we are still doing the same test. Our null hypothesis is that mu is 0.5. Our alternative is that mu is less than 0.5. Okay, and this is all we have. I have the p-value, I have the alpha, and I have my test. Can you tell me how you conclude about rejection or fail to rejection of the null hypothesis using the p-value? If this is the z table, and this is here minus z alpha, this black shaded area is basically what we have as alpha. And here, z of alpha is minus 1.65. And then the value of our test statistics ended up to be this number, minus 1.06. Okay, so that's the value of the test statistics, Z naught. And then the p-value is basically this red area. That's what the p-value represents. Now, if p-value is greater than alpha, which is the case here because p-value is the red area, alpha is the black area. If p-value is greater than alpha, then we are in this region. We are in the blue region. And this blue region is fail to reject H null region. So if p-value is greater than alpha, you always fail to reject H null. And that's the case here. The p-value is 0.14, the alpha is 0.05. So here, since exactly in this problem, 0.144 is greater than 0.05, so the p-value is greater than alpha, so we are going to fail to reject H null. And we have to for sure get the same conclusion that we got using the previous method, using the test statistics directly and comparing that with the critical value. We got the same conclusion as well. Fail to reject, fail to reject. One of them is using the p-value concept and comparing that with the alpha. One of them is using the test statistics concept and comparing that with critical values. But both of them have to give us the same conclusion, which they did. Okay. Any questions so far? Okay. Let's go to question 2. And for question 2, I want your help, guys. You are going to help me to do that. For question 2, the oxygen concentration in streams below 20 dams have been measured in milligrams per liter. So that's the oxygen concentration. And we know the values of these 20 samples. 5, 3.4, 3.9, 1.3, all the way to 6.5. So we know the oxygen concentrations in each one of these 20 samples. Water quality engineers are interested in knowing whether these data support a claim that mean dissolved oxygen concentration is 2.5 milligram per liter or not. Formulate the appropriate hypothesis. So the characteristic of interest or the random variable of interest here is oxygen concentration in the water in a dam. And we took a sample of size 20, n is 20, and we have the value of each one of the samples, these 20 values. And we want to test the hypothesis that if the average oxygen concentration in a dam is 2.5 milligram per liter, or this is not the case. Okay. Now, tell me that from these 20 samples that we have gotten, and we have the values of these 20 samples here, what are the two things I can get from this sample?
The sample size, the average,
So if you have a sample, what are the things? We had that conversation here, right? If you have a sample, we said we use X bar for mu, and what do I use for sigma? To estimate sigma?
S.
S. Okay. So if I have a sample and I have the data of the sample, I can not only calculate the average of the sample, but I also can calculate the standard deviation of that characteristic of interest in the sample. If we see the problem statement, in the first 4 lines of the problem statement, it doesn't tell anything about the standard deviation of either population or sample. It doesn't say anything. So if it doesn't say anything about the standard deviation of population, so sigma is not known, then I have to use my sample to calculate X bar and to calculate the sample standard deviation. So in a lot of problems we looked at so far, or the examples, always I give you these two. I say, oh, we took a sample of size 20, sample average is this, sample standard deviation is this, but that's not the case in a lot of real world problems. You are the one who goes and collects the data or get the data from somewhere, and then you have to calculate the average of the sample and the standard deviation of the sample. And we went through, we had a similar example in previous session. So you guys saw the formula for standard deviation. So using the same formula, in this example, average of this 20 sample is going to be 3.265, and a standard deviation using that formula, if I use that, is going to be 2.127. Okay, so now I have a sample of size 20. I've calculated average of the sample. I calculated the standard deviation of the sample. So, and then I need to test this hypothesis. Okay, what is the very first question that you have to ask yourself when you see a test of hypothesis problem, when you read the problem? What is the very first question?
Like if you're using, or like if you have the standard deviation or not, and if it's known.
Exactly.
And if
the
it's not,
first question always.
Something else.
Do you have a standard deviation of the population or sigma known, or it's unknown? Always. For a confidence interval or test of hypothesis, that's always your first question. Here, in this example, do I have the standard deviation of the population? Why do you?
No, we don't.
Only with the sample.
Don't. The problem didn't say anything about the standard deviation of the population. That's why I calculated the standard deviation of the sample from these 20 samples I had. The problem didn't give me a standard deviation of the population. I do not have the standard deviation of population. I calculated the standard deviation of the sample, and I'm going to use S in my formulation. So if I don't have a standard deviation of the population, I do not know sigma, then I have to use the formulas on the right side of this screen. The T0, so this is the one I have to use to calculate the test statistics. So let's go back. Okay, so if you make that important recognition at the start of the problem, that's basically is going to save you, because then you won't use the wrong formula or anything. So when you also put your cheat sheet together, guys, make sure to specify those. Okay, these are for scenarios when I know the sigma. These are for scenarios when I don't know the sigma. Then you don't pick the wrong formula based for the problem. Okay, so here I don't know sigmas. I have S. So the test statistics or T null is going to be calculated by X bar minus mu divided by S over square root of N. And that's going to be 3.265 minus 2.5 divided by S 2.12 over square root of N, which is 20 here. And the value is 1.608. Okay, so this is my test statistics. Now, I want to make a conclusion about these tests. So I have to compare the test statistics with T of alpha over 2 n minus 1 or T of alpha minus T of alpha over 2 n minus 1. I have to compare the test statistics to one of these. And obviously here, since my test statistics is positive, then I don't need basically this second comparison. I don't need that. So the only thing I need is this one. But anyway, so let's go to the T table and find the T of alpha over 2. Alpha here is alpha here is a 0.05. So alpha over 2 is 0.025. So T of 0.025 and n minus 1 is 20 minus 1, which is 19. So what is the T for this one? So guys, if you don't have the T table open, please go to module 8 and open the T table, because as I said in previous session, it's very, very important for you guys to be able to correct the right value from the T table. If you have all the formulation correct, if you pick the you do the right decision. Do we have sigma or not? You pick the right formula, but you cannot find the right t value from the t table. Everything else is going to go wrong. So go to the t table, please, and tell me what is the value of this. What is this t value that I'm looking for?
I tell you now. I haven't.
What did you say?
I have it. I have it. Do you want me to tell you?
No, just let's give a little
Give
time.
me a second.
T of 0.025 and 19. Can someone other than Serena tell me the number? What's going on, guys? Okay, what is the value, Serena?
2.093.
2.093. Okay. Remind me that after this problem, I don't want to disconnect my iPad, so remind me after we finished everything to go over the t-table once and maybe we find one value, because all of you really should feel comfortable finding the numbers from the t-table. Okay, so this is the t value, and then I need to compare the value of my test statistics with this t value. And if the value of test statistics is greater than this t of alpha over 2 n minus 1, or the value of test statistics is less than. For a two-sided test, if these two conditions hold, then, or one of these conditions hold, then we reject. Right now, the value of the test statistics here is 1.608, and the critical value is 2.093. So this is T naught, the test statistics, and this is the critical value. As you can see, the test statistics is less than critical value. So since this condition does not hold, then we fail to reject H naught. And so that's basically the conclusion here. And as you can see, did we do that? No, we haven't done that using the clipboard. Okay, that's the conclusion here. And I want you guys in part C, I want you guys to calculate the confidence interval as well. And for the confidence interval for mu, if I don't know the standard deviation, I mentioned the formula in previous session and you know that formula from the videos as well. The formula is x bar minus t of 0.025 and 19 s over square root of n x bar plus t of s over square root of n. And if we replace the numbers, x bar is going to be 3.265 minus 2.093 multiplied by s 2.12 divided by square root of 20 less than or equal to mu less than 3.265 plus 2.093 and s, which is 2.12 divided by square root of 20. And this is 20 or 40? 20. And when we do the calculations, the final number is 2.270 less than or equal to mu less than or equal to 4.26. Can you tell me that if this is the confidence interval you have for the mu and we still want to test our hypothesis? Null says mu equals to, what's the value? 2.5. Alternative says mu is not 2.5. So still, this is the hypothesis test that I want to run, and this confidence interval is all I have. Can you make a conclusion about this test given the confidence interval, and tell me why?
It's in between the intervals, or I guess the 2.5 is in between the intervals, so fail to reject.
Yes, so the value that we want to see if it's correct or not, the 2.5 is in this interval. So basically this interval says that this is a 95% confidence interval. This interval says with 95% confidence, this unknown average that I'm looking for falls somewhere in this interval between this number and this number. I don't know exactly what is the value, but it falls somewhere here. So then if someone asks you, what do you think about average being 2.5? Okay, 2.5 falls in this interval. It's between 2.2 and 4.2. So the 2.5 falls in this interval. Then it can be the unknown average potentially. So if the hypothesized value, if this hypothesized value for the average falls in your confidence interval, then you fail to reject your edge null. You fail to reject null hypothesis. You don't reject, you fail to reject. So, and we had one example in previous session as well, and that's how we can use confidence intervals to make conclusion about the hypothesis test. So as you can see, we can make conclusion about rejecting or failing to reject a null hypothesis using the confidence interval. You can make conclusion about rejecting or failing to reject a null hypothesis using the p-value and comparing that with the significance level, or you can just calculate the test statistic here, for example, and compare that with the critical value, which we did here. Just the traditional classic method of answering the test of hypothesis question. And all of them lead to the same answer. So when you guys prepare for the exam, make sure you guys are comfortable with each one of them, because in the exam, I may give you a test of hypothesis. I give you, for example, the confidence interval. I give you the lower bound and upper bound of the confidence interval, and I tell you, okay, make conclusion about accepting or failing, about rejecting or failing to reject the null hypothesis. So you just have to know how, if you have confidence interval, how you would make conclusion about rejection or failing to reject a null hypothesis. Or similarly, I may give you a hypothesis test. I may tell you, oh, this is the hypothesis that we want to test. And then I may tell you that, oh, we took a sample of size and we calculated the average of the sample. And finally, the p-value associated with our test statistics is this much. What would you say about this test, given the fact that alpha is this? So then you have to be able to decide on rejecting or failing to reject the null hypothesis just by knowing the p-value. So you have to know how to make a conclusion if you know the p-value. Or like the method that you have seen in the examples a lot, where you have to calculate the test statistics, Z0 or T0, and then compare those with the critical values and so forth. which is just another method. Okay, but all these three methods should give you the same answer. So make sure you're comfortable knowing how to use each one of them. Confidence interval or p-value method, or just a classic test statistics method. Okay. Okay, guys, the question 3 is related to the power of the test, and everything you need is given in the problem statement. And this is for module 7. In module 7, in the video that I posted, I have examples similar to that. So I'm going to pass that one. Make sure to do it yourself. If you have difficulty, I hold my office hours 4 to 5 today, and feel free to email me before next Thursday, which is your exam, to find the answer. I'm going to pass it just for the sake of time. We have only another 15 minutes to go. And I want to go to question 4 that's related to proportions. So I want to also go over one example related to proportions. So let's do that. Okay. Question 4. So here we want to test. So we have a characteristic of interest in the population, and the proportion of this characteristic of interest is what we want to test. So our test is that our null hypothesis says that P, the proportion of characteristic of interest, is 0.6. And our alternative says that P is less than 0.6. And these are a bunch of information that we have related to this problem. I have N. Can someone tell me what is N? What is the meaning of N? N is 494, but what does it show?
Number of experiments.
Can you say it louder, please?
Number of experiments.
Number of experiment, or basically our sample size. Okay, so that's we take a sample of size 494, or we repeat this experiment 494 times. Okay, so that's sample size. And what does X show here? If you're talking about portions, right? So what does X show here? Remember, at some point we do X over N to calculate something. What does X show?
Is it like the number of successes?
Exactly. X is the number of success in N sample, or N experiment. Okay. So let's assume this proportion is, I don't know, since I like NBA, this is the proportion of people who will watch NBA in December when the season starts again. So we take a sample of 494 people and we ask them, are you going to watch NBA games when they start again? And 287 of them says yes. Okay. So then if I calculate X over N, what do I get? Do you remember the notation for this? Or even don't forget about the notation. What would you get? You pick 494 people from the US population, 287 of them say we will watch NBA. What would you get if you divide 287 by 494? What does that number mean? That's easy, guys. What is it? So this is 58. 58.58. What is the meaning?
It's a sample proportion.
Okay, what does that mean? In the example that I gave, what does that mean?
It's like the percent of successes.
Exactly. So it says it's the percentage of success in the population. In this example that I just gave you, the success is defined if they watch NBA games. So I asked them, 287 of them say, oh, we watch. So then this gives me the proportion of the population or the proportion of this sample that will watch NBA games. Okay, so this is a sample proportion. And the proportion of sample that reacted successfully to whatever question or experiment we are performing. What is the notation for this? Is that p hat? So that's sample proportion. The notation for that is p hat. You have to, that's the same notation that has been used in the video, right? Can you confirm?
Yes, it was.
Okay.
Yep. What is the delta that they use in the equations that you have in the reference sheet? What is that? Because I feel like it's a different notation from the videos.
Where did I use that?
It's not. You didn't write it down here, but it's on the reference sheet.
I used reference sheet. Where did you get reference sheet from?
The reference sheet, you have it posted somewhere.
I didn't post any reference sheet.
I think it's in the module 8. Module 8 reference sheet about like all the different hypothesis tests.
I think that you're talking about the difference between when we want to calculate beta, the type 2 hypothesis. That's the difference, because when we want to calculate, okay guys, just hold on the examples we were going to. Can you keep your question, Serena, for the end?
Yeah, sure.
Don't forget the question, but because that takes me to type of 2 error and things, so I want to make sure to finish this and then I'll go to that, okay? Make sure to ask your question when we finish.
Sure.
Okay, so let's continue with that. So, okay, so this was the notation that was used for sample proportion. Okay, now I wanna test if the proportion of this characteristic of interest in the population is 0.6 or not. The test statistics that we have is it's called Z naught, has a T distribution, has a Z distribution, and it's X minus NP 494 multiplied by 0.6 multiplied by 0.4, 1 minus 0.6. And when we do this, when we do the calculations, Z is going to be minus 0.863. So that's going to be Z and the value of the test statistics. And here we have a one-sided test, and the value of the alpha is still 0.05. So I have to compare the test statistics with minus Z of alpha. And if the test statistics is less than minus Z of alpha, then I'm going to reject null hypothesis. So here, minus Z of 0.05, and since this is a one-sided test, you see this is a one-sided test, I use the whole alpha. I don't say alpha over 2 or anything like that. So minus Z of point alpha, so that's minus 1.65, and the test statistics is this value that we have. So the test statistic is minus 0.863, and the critical value is this. Is the test statistics less than critical value or greater than critical value? You're comparing this value with this value.
It's greater than.
Greater than.
Greater than critical value. So since this relation does not hold, then
It's fail to reject.
we fail to reject. Okay, so construct the test test statistics, compare it with the critical value, make sure to pay attention to see if it's a one-sided test or two-sided test, compare it with the critical value, and make the conclusion. And now, I want us to also calculate the p-value. So let's calculate the p-value here as well. So the p-value is probability of, since this is a one-sided test, upper bound is probability that z is less than our test statistics. So that's probability of z less than minus 0.863. And I want to calculate that. So z less than minus 0.86. Minus 0.8 is this row here. 86 is this. Minus 0.19. Okay, so that's the probability that I obtained from the z table for this probability. So that's my p-value, and my alpha is 0.05. Make a conclusion about this test. You only know the p-value, you only know the alpha. Make a conclusion.
It's if p-value is greater than alpha, then you fail to reject.
Yeah, if this always works for any type of test. If p-value is greater than alpha, we always fail to reject null hypothesis. So here my p-value is 0.19 and my alpha is 0.05. P-value is greater than alpha, so I fail to reject. And that's the exact decision that I also came up with using the test, just comparing the test statistics with the critical value method. The p-value method gave me the same result as. And let's do the confidence interval method too. Let's construct a confidence interval. So if I want to construct a confidence interval here, since this is a one-sided upper bound, the formula is p is less than or equal to p hat plus z of alpha divided by n. Okay, so that's the formula for confidence interval. I didn't do any tricky thing, nothing. P hat we already know. That's the sample proportion, that's 0.58. Z of alpha, also we know that Z of 5%, that's 1.65. So P is going to be less than 0.61. Okay, so that's my one-sided confidence interval, and this is the test that I wanted to run. Given this confidence interval that you have constructed, this 95% confidence interval that you have constructed, make a conclusion about this test. What is the rule? When you have a confidence interval, tell me, just forget about this problem. Tell me the rule. If, for example, the P naught or mu naught falls in the interval, what is your conclusion?
You would fail to reject the null.
Exactly. If P naught or mu naught falls in the confidence interval, then if P naught or mu naught falls in the confidence interval, then we fail to reject H null. Why? Because here, what I say is that with 95%, I'm confident that this proportion of this characteristic of interest that I don't know its value. However, I can say with 95% confidence is somewhere less than 0.65. I don't know exact value, but it's somewhere less than 0.65. But then I ask you, look, I'm testing if this value is 0.6 or not. okay, 0.6 is in this interval, it's less than 0.61. Then if you are testing that it's 0.6, and I'm telling you with 95% confidence is less than 0.61, then you don't have any evidence to reject the null hypothesis. Okay? That's why we fail to reject the null hypothesis in this scenario. So again, make sure you guys are feel comfortable with making decision about the hypothesis test if you know the confidence interval, if you know the p-value, or just the classic method of knowing the test statistics and comparing that with the critical value. Make sure you guys are comfortable with any one of those. The next question says a new technology. Okay, before I go, any question, guys, so far? I know it's past the class time, but I'm going to just go over the last question as well. If you need to leave, feel free to do so. I'll post the video later. Okay. A new technology for the production of integrated circuits is being mastered. The technology will be rejected if the percentage of defective integrated circuits exceeds 0.1. So our null hypothesis is that P is these. Our null hypothesis is that, and our alternative is that P is greater than 0.1. How many integrated circuits has to be checked to make sure that the technology gives a sufficiently small amount of defects with a probability of 0.1% if the actual probability is P equals to 0.05. Alpha is 0.005. So if we look at the formula for calculating the sample size in a one-sided hypothesis test for the proportion, the formula is, so then here P naught is actually this value here. That's always P naught or mu naught. So we know that. Then P is the actual value. So P is the actual proportion or probability, and here the actual value, the actual probability is 0.05. It's given in the problem statement in the last line. If the actual probability is 0.05. So the P is given to you as well. Z of alpha is identified. If I know alpha, we know the alpha, thus we can calculate Z of alpha from the table and put it in this formulation. The only other thing I need to find is Z of beta. And remember, beta is probability of failing to reject the null hypothesis if the null hypothesis is wrong. So it says how many intervals have to be checked to make sure that the technology gives a sufficiently small amounts of defects with the probability of this if the actual. So basically, if you read the last two lines, it tells you that the probability that we find the chance or the probability of number of defects is 1%. So the last two lines tells you basically that the chance of failing to reject H null if H null is not correct. if H null is not correct here is given to you with saying you that if the actual probability, actual P is 0.05. It says if the actual probability is 0.05, then the chance that we are going to fail to reject the null hypothesis is 0.01. With 1% chance, we may fail to reject the null hypothesis, and that's exactly the definition of beta. So the last two lines basically have given you what is beta. And if you have beta, then you can put that in this part of the formulation, and you have everything else. You have the P, you have the P naught, you have C of alpha, you can find C of beta from the table, given the fact that beta is given to you 0.01, then you can calculate N. And if we do the calculations, N is going to be 1924. You can do the calculations yourself and see if you get the same number. I think the only tricky part in this question is how you read the last two lines and make the conclusion that that's beta. But generally, for module 7 and 8, as I said, the main thing that when you read a question, make that first important decision. If I know standard deviation of the population or if I don't. And when you write your cheat sheet, make sure to write the formulas clearly for the scenarios where I know the standard deviation population or not. When you make that distinction, then make sure to pick the right formula depending on if you know sigma or not. Pick the right formula. The rest is just plugging in the numbers. Problem statement should basically give you everything you need. X bar, sample size, standard deviation of the population or the sample. So the rest is just plugging in those values in the right formulation. And the only other thing that you guys need to do on your own is making sure that you can find the correct value for the Z and the correct value for the T from the Z table or the T table. And that's it. Otherwise, there's not much, honestly, tricky thing going on with these concepts. And also, as we went through a couple of examples today, make sure you feel comfortable with making decisions about a hypothesis if you know the p-value, if you know the confidence interval, or if you just look at the test statistics. Make sure that those parts are clear for you as well.